everybody, and welcome to our second round of events in which we are looking to foster the dialogue between our two research groups, Katja and mine, and therefore on a larger scale, the dialogue between the history of ancient and medieval philosophy on the one hand, and modern science and its history and philosophy on the other side. We had a first event last fall, but this one is going to be the first one that deals with a main theme of this series with events, or the main theme. And those are the questions in the title, the scientific questions, and not just any scientific questions, but the really big questions, like in this case today, the question, how did the world come into being? So since this is the first session where we deal with these questions, I'm going to say a bit more about the role of those questions play for our vision of this event and for our thinking about it. And I think there's two reasons why these questions are so central to our thinking and also appear in the title of these events. The first one is that these questions, these big questions, like how did the world come into being, certainly played a central role historically over time. The exact role, I think, is something that we want to work out more clearly, but it's also clear that in the polarized debate on science in these days, certainly these questions seem to fall by the roadside. If you look at the two caricatures of the extreme views on science, we have on the one hand science as an instrument of power and hegemony, and on the other hand, science as these hard and fast rules that we need to live by if we want to survive, be it the climate crisis or the pandemic. But both of these extreme views tend to ignore the seeking and philosophical aspect of science that is embodied in these questions. What exact role these kinds of questions have played in history, whether they were just window dressing or the main engine of development in science, is an open and empirical question, and one that we wish to explore in this series of events. So what role did these big guiding questions that are often invoked, what role did they play in ancient times all the way to modern scientific inquiry? On the other hand, these big questions also play a methodological role for our historical inquiry. Because if we look at these kinds of comparative longue durée studies of reaching from ancient and medieval philosophy to modern science, we do, of course, see these kinds of questions recurring. We definitely see people asking the question of how did the world come into being in ancient times to today. But the historian's knee-jerk reaction there is to say, well, these questions might look alike superficially, but the words don't really mean the same thing. They're working in very, very different frameworks. You might even want to invoke Kuhnian incommensurability here. So this kind of resemblance of the big questions over time might just be superficial. Now, if you just look at the questions, that's kind of hard to argue against. And certainly to some extent, it's true that the words like being or world meant very different things to the people asking that question. But we're not going to be looking just at the questions today, but also at what were considered potential answers, or what are considered potential answers today. And then once you have the questions and the answers together, you can start thinking about the fit. And you can ask questions like, are the answers being proposed to these questions by modern science, would they in some translated or translatable form have been considered answers to those questions as asked by natural philosophers in antiquity or the Middle Ages? And then you can start talking about how incommensurable are these questions, really the words being used in them? Is translation possible? What are the concrete obstacles to translation, rather than just submitting to some vague ideas about, well, these are different worlds and we can't really translate between them. So that's what we're also trying to do here today, address these questions of continuity in the longue durée by actually looking empirically at a dialogue between those people who are looking at how those questions were being answered in the past and those people who are trying to answer those questions today. what's at stake here? Of course, there's a historical question at stake, namely about the transformation of knowledge in the longue durée. But there's also a very concrete question about the role and import of these practices, both the study of ancient and medieval philosophy and the contemporary practice of science. There's the question to what extent both of these practices are part of an overarching human project of trying to answer these big questions. That's important for the study of ancient and medieval philosophy. Are the answers given there, the questions posed, the thoughts raised, still relevant to our thinking about this today? And it's also relevant for modern science in the sense that the question there is modern science really trying to answer these big questions that have been with humanity for millennia, or are they just packaging their very specialized research in these philosophical questions? So it's really also about the existence of these questions as big projects of humanity. Are they just things that have recurred because they're somehow, they seem vaguely attractive and can be used to motivate research, or are they really the driving forces in our intellectual inquiry over the centuries? And that's what we want to see today. And we have some very wonderful guests who are going to present the attempts to answer those questions from ancient times to today. And for that, I'm going to hand over to Katja.
Thanks so much, Alex, and welcome to the speakers, especially Jean-Luc Lehners, Alberto Ross, Michael Chase, and Maria Cortez, also from my side. Today, I will be chairing this entire session and lead you through our 4 talks that we have and the discussion at the end of our meeting in the evening today, at least in Berlin. I know that some of you are not in Berlin, but very far away. On a different continent. Now, let me dive right in and introduce the first speaker of today's session to you. So our first speaker today on the first big question that we will be covering, which Alex has so aptly introduced, creation, or how did the world come into being, is Jean-Luc Lehners. Since 2010, Jean-Luc Lehners has been at the MPI for Gravitational Physics, the Albert Einstein Institute in Potsdam. And he's currently heading the ERC research group, Theoretical Cosmology. It's a consolidator's grant. He studied physics and mathematics at Imperial College London and the University of Cambridge. In 2005, he completed his PhD on brane worlds in supergravity, and brane here is spelled B-R-A-N-E. He held postdoctoral positions at the University of Cambridge, at Princeton University, and the Perimeter Institute in Canada. Jean-Luc's research concerns the early universe and the time of the Big Bang. Quite aptly, therefore, his talk today will be about the Big Bang and quantum gravity, current ideas about ancient times. It is a great pleasure for me and for all of us organizers to welcome Jean-Luc Lehners today. The floor now is all yours.
Okay, so thanks very much for the invitation to give a talk here. I'm very happy to be able to join this symposium and this mixture of physics and philosophy. And so I will be presenting basically the viewpoint from physics, trying to present the current view from theoretical physics about sort of the current thinking about the creation of the universe. Now, the thing is that in the last 100 years or so, physics has really made some discoveries that have completely changed the way that we think about the universe. Until about 100 years ago, the idea was that time and space were an arena in which everything happens, and matter was present in this arena, but matter was essentially moving around, but not really changing in its essence. Now, all of this, what I just said, is essentially known to be not really true anymore. And so let me explain in what sense. I think the first real discovery that changed our viewpoint of the universe was the discovery of the expansion of the universe. Now, the fact that the universe expands is best explained not by the fact that galaxies just move apart in a pre-existing space, but in fact that the space in between faraway galaxies expands. So, or put differently, new space is actually created in the universe, is created due to the expansion. Now, space therefore loses this aspect that it is an absolute a grid, on which it happens, an arena. Space is not absolute anymore. Space can evolve. And in fact, new space is created every day, as far as we know. Now, there are many pieces of evidence for this. The main one in which this was discovered is the redshift of galaxies that move away from us. Let me just give you one piece of evidence, which is that if you think back in time, the universe must have been smaller, denser, hotter. And we have good evidence that this was indeed the case. So in fact, there was a time when the universe was so hot that even atoms did not exist, but electrons and protons were flying around freely. Electrons had so much energy that they were not bound to nuclei or to protons. So, and at that stage, photons could not really travel very far before running into an electron. So photons constantly bounced off free electrons, and the universe was not transparent. As the universe expanded and cooled, the first atoms formed, and at that stage, the photons, the particles of light, did not interact so much with these neutral atoms anymore. And suddenly light could fly freely through the universe. And so at that point, in a sense, radiation was released in the universe, and this radiation is still around. And this is known as the cosmic microwave background radiation, and it can be measured. Here is an example in false colors, because this radiation is at a wavelength which our eyes cannot see, but it can be measured with satellites. And here is an example of the Planck satellite measuring tiny differences in temperature, or tiny differences in wavelength in this radiation. There are some more pieces of evidence. For example, the abundance of light elements in the early universe can be calculated if you assume the universe is expanding. And this also agrees very well with observations. Now, relativity, furthermore, implies that space and time link together. And so we find that space and time really are evolving. Moreover, their evolution is linked to the amount of matter and the type of matter that is present in the universe. In relativity, space and time and matter are linked together. And now if we go back in time, from the fact that the universe is expanding, now if we go back, we find that the universe was smaller and smaller. And if we go back as far as we can, if we extrapolate as far as we can, everything becomes infinite. The universe becomes infinitely small, the curvature and temperature become infinitely high. And this is what we call the Big Bang. Now, the question really is then what happened at the singularity? And there's two main options which are often discussed. One is that, the Big Bang was the beginning of the universe, the creation of the universe. And the other one is that the Big Bang was some kind of transition from a prior phase. So you could imagine that the universe was in a phase of contraction before. I mean, if the universe can expand, it can also contract. And that there was some kind of reversal from contraction to expansion. Now, before discussing these further, I want to just introduce some ideas which come from quantum physics, because this adds a new twist to all of this thinking. Because quantum physics really tells us that events only have a certain probability of happening. And in fact, many other things get changed. So for instance, particles in quantum physics have no permanence. Particles can change, what I want to say is that particles have in a sense, no real objective meaning. The number of particles can change depending even on who looks at it, depending on the observer that looks at it. The particles nature and number can change. And the only reason why we don't see these effects in ordinary life is that for large systems, typically the dynamics becomes more and more like that of classical physics. One can show this. And, but really fundamentally, quantum physics behaves very differently. Now, some other aspects of quantum physics is that, in a sense, quantum physics forces you to use very strict logic, that you can only talk about things that really can be observed or measured. Now, if you take this seriously, then it is, in fact, it doesn't really make sense to talk about something that's infinite, because infinity can never be measured. Now, if you now go back to this idea that the universe, that the Big Bang was really a big bounce, that the universe was, that if you have a singularity, it gets replaced by a bounce and the universe continues beyond this, then, if this happens at all singularities, then the universe is, well, first of all, non-singular, but it is most certainly infinite then. Because there is never any place where space or time could end. And then you get infinities, and this is simply something which you can, even in principle, can never verify. So I think this is simply unphysical, and to me, it suggests very strongly that this is not what happens. In fact, if you really look at quantum physics in detail, only things that are finite actually make sense. And so the conclusion would be, or the extrapolation would be, that also time and space should be finite. Now, if you combine all of this together, relativity and quantum theory, then the conclusion would be, or the suggestion would be, that time, space, and matter have no permanence. And moreover, that their description depends on the observer. And in fact, the theories of quantum gravity that are under development really suggest that this is true. Now, then the reason why we would see time and space and matter as so classical is just because our universe at the moment is very large and has a lot of stuff in it. And so that would mainly be the reason for why the universe appears so classical. But if we think about the creation of the universe, then it's a very different matter, and we have to take quantum gravity effects into consideration. The question then is, what could the creation of the universe look like according to quantum gravity? So I just want to give you two examples of descriptions that have been put forward, or that could bear, well, anyway, they're just two possibilities. One should say from the outset that our understanding of quantum gravity is certainly not complete. And so anything that we think about strong quantum gravity effects is necessarily preliminary. It's just something that we are trying out at the moment. It is certainly not a definitive answer. Now, one framework which I find particularly interesting is the no boundary idea of Jim Hartle and Stephen Hawking. And the idea they had is that you don't go to the singularity. So if you go back in time, you look at the geometry of the universe becomes smaller and smaller, but you don't continue all the way to the point where everything becomes infinite. Rather, their proposal is that the universe is smoothly rounded off. Such a rounding off of the geometry, then replaces the singularity, and that would be the effective Big Bang. What is interesting about this is that this rounding off cannot occur with purely real time. It kind of requires time to become a bit like space. And the way in which this happens mathematically is that, in fact, this is really describing the quantum state of the universe. So if you make this restriction, that if you force the theory the geometry, if you force the geometry of the universe to be smoothly rounded off, basically it gives you a prescription for calculating a quantum state of the universe. It gives probabilities then for different histories to occur, just as you would expect from a quantum theory of gravity. Moreover, this same proposal can explain why the universe became classical. So it can explain how the universe started in this quantum state, but then behaved more and more classically. And moreover, the amplification of small fluctuations, again by quantum effects, can explain the origin of structure in the universe, the origin of why in certain parts of the universe matter arose and clumped together, and why in other parts the universe is empty. Now, one should say that this is not a full description of physics. It is, in a sense, a proposal for boundary conditions. So given a physical theory, it tells you how to calculate the corresponding quantum state of the universe. If you take a different theory, in that theory, it will tell you again how to calculate the quantum state of the universe. So this is an important aspect in the sense that it's not enough to just discover a theory of physics, what is the correct theory, but also what is the correct solution. So in a sense, this is a prescription telling you what solution to consider given the theory. The question that still remains, though, is what is the correct theory? And this is really where also in the last 2 or 3 decades, much progress has been made. And we know that they can, and quantum gravity seems to suggest that actually the universe is made of quite different constituents as what used to be considered. And so let me briefly review string theory. String theory is the best candidate theory we have of quantum gravity at the moment, but it describes physics in terms not of point particles, but in terms of strings. So little one-dimensional strings which vibrate, and different vibrations would correspond to different particles. In this way, it manages to unify different particles to get, into one coherent framework. And these strings can move around, especially if they're closed, they're like little ribbons. They can move around everywhere in space-time, but they can also be open, and the endpoints can be attached to higher dimensional objects, which are like membranes. They can be membranes that have 2 dimensions or more, 3, 4, 5, and so on. In fact, the whole of space-time, typically, as I'll explain in a moment, but the whole of space-time has 11 dimensions. And so in this space-time, you can have various membranes, also various dimensions. And so this physics is described in this much more general framework. An important aspect of this theory is something called duality. And this is something really new to string theory, or different from earlier physics. And it's a very particular quantum gravity effect, which might be important in understanding the Big Bang. Now, the thing is that these dimensions, if there are so many dimensions, then, and clearly we don't see all of these, then the idea is that some of these dimensions could be small, in the sense that you cannot keep going forever in one direction, but they could be a bit like a garden hose, for instance. So it could be circular, and then that dimension, if it's very small, then if you go a little way around it, you come back to where you started. That means that, but the fact that now there are strings in the theory means that some of these strings can also go all the way around this dimension. These are called winding strings. The surprising thing is that if you look at this situation and you look at the physics, if you take strings that do not go around, then they see a dimension that has a radius r, say. But now you describe the same situation, but you look at the winding strings, then one notices that they actually see a radius 1 over r. So if the universe is small, considering the normal strings, let's say, then from the point of view of these winding strings, the universe is very large, and vice versa. So under some conditions, one or the other type of string can be the more appropriate object used to describe the universe. This shows then again that reality depends very strongly on the point of view of the observer. And these dualities then actually imply that our current universe could be just a phase of the universe, and that a prior phase could be described by a dual theory, that could be involving very different physics. And so then the Big Bang would actually be, the creation of our universe would really be kind of a transition from a very different phase of evolution. The thing in that case is that, effectively the laws of physics would change from one such phase to another. And so what you end up with is that then the sort of general overview would be that you have all sorts of different domains, which all have different effective laws, different fundamental objects, and even different dimensions of space. At this whole framework, I should say, is only understood to a very small degree at the moment, but it is what string theory suggests. Still, in all of this, let me come back to just what I think is sort of the main riddle that quantum gravity gives us. And it is a bit like one of these Zen koans, really, that, you know, when we think of creation, we think of it as a process occurring in time. I think that our brains are kind of hardwired to think of it in that way. Yet time itself has to be created. And quantum gravity is very clear on this, that time is not fundamental. It has to be created. It can, under certain circumstances, behave classically, so to speak. But this, you know, how to reconcile these things, I think, is something that, you know, is something that can, well, gives you a lot of food for thought. But it is a riddle that needs to be solved. Thank you.